It's good. So I'm glad to hear that I now have 45 minutes. Thank you. It's nice to see all of you again in this. I think it's the first time I do a presentation seeing the sea through the window, actually, so I better not look too much. This is, in fact, those results are quite old, in fact, and we wanted to present them at the last edition of this conference or workshop, but we didn't really have time. And this is the work of Pablo Lorenzino, who was a postdoc at that time in Lyon, and I met him in Malaga, in the Malaga edition, so this is where I recruited him, and so those workshops can also be useful for that. And this is some work we did with Catherine Verdu in Lyon, but I could have also added Franck somewhere, because this is a research project, I mention it later, which has been initiated by Franck, and he was the PI on that topic. So we had some, at that time we had some interesting but intriguing results on the 3D shape of cracks growing in forged steels, and we thought that we missed a good opportunity to discuss that with the community. And then we went back to INSA, did more experiment, and now we think we have a sort of understanding of what's going on, but I think it's still an open question, so maybe we'll have time to discuss it now. Well, obviously we have time. I now have 45 minutes. Okay. So I work in Lyon at INSA in Mateus. So just maybe two very general slides of introduction about forging, a very well-known process, producing a large variety of components. Those ones are small, but you can also produce very big parts like this. And this is, of course, a process which has a dramatic effect on the microstructure. Some of them are listed here. It's not exhaustive, right? And sometimes also forging is followed by surface hardening or some other kind of surface treatment. So that was really the aim of this research project that Franck set up in France with several labs and some industries, forging industries and car industries. And the basic idea, you can correct me, Frank, if I'm wrong, but that was the influence of the forging or the process on the fatigue properties. So just to illustrate maybe what can be the influence of the finishing process, for example, on the microstructure. This is a slightly different process, but I think it gives a good idea. This is hammering, which is tapping on a weld to improve the fatigue properties. So you see optical micrograph of the structure. It's ferritopyrolytic steel, and it's within, close to, but not in the heat-affected zone. This is, you can see that the size and the shape of the grain is changing. This is the corresponding EBSD map with some very small grain at the surface, and this is the kernel measurement telling you that you indeed stored a lot of plastic deformation, dislocation close to the surface. And of course this has an impact on the surface hardness, which falls off quite quickly, but it falls off to a bulk level here after, say, 0.5 millimeter. So the surface finishing has indeed a large influence on the microstructure. And then the question we wanted to address was, okay, we have a surface gradient. How can this affect the propagation of the fatigue cracks if they're small, right? Is it large enough, this gradient, to have an effect on it? So again, this is the research project led by Franck. It was called DEFISURF, funded by the French Agence Nationale pour la Recherche. I keep advertising, so that they will probably give us more money. You never know. I will first describe the materials and what we did in terms of methods quickly, then some results. Don't expect too much in anything very spectacular. Unfortunately, they are a bit boring crack fronts, but nevertheless, I think it's interesting. And then I will try to discuss what we saw, and this is, I think, where we need to exchange if we think we are correct in the assumptions on. So there are two types of components, or two types of samples that we have used. Some samples we have extracted from forged parts, connecting rods in that case, and they are extracted directly from the components. They've been hot forged, and some of them have been shot blasted. I'll come back to the shot blasting process after. And those which are not shot blasted are just brushed to remove the scales from the forging process. Other samples have been extracted from extruded bars with two different strain levels, 18 and 17%. So they're extruded, and then you extract the sample from the skin of those bars. So this is a summary of the materials. They are all steels. Two of them are low alloy steels, very topologic in those cases, and two are not alloy. Those two ones have been hot forged, respectively, in hot forged plus shot blasted, and the other one have just been cold forged to different strain level, as I explained before. They are relatively high strength alloys with yield stresses ranging from 800 to 1000 gigapascal. Grain size is fairly common, except in that one where there is a grain size gradient. I will show that later. So I will name those material 1, 2, 3, and 4 with the Roman numbers here in the rest of the talk. Shot blasting, it's something which is used in the case of those components. You just put your connecting rods in a big barrel and you rotate the barrel. So by rotating and with the different contacts between the components, you improve the surface finish and you improve the fatigue properties. It's very time effective, and when you stop rolling, you get everything out, and you can do a lot in a short time. But to be honest, I think there is hardly any control of the process. It works. So, what does it give? In terms of microstructure, this shot blasting process has a dramatic influence on the grain size, and this is shown here. This is an EBSD map showing the grain size evolution between the surface and the bulk. I'm showing here roughly 150 micron. This is the scale bar here, and you see that at the surface, by the repeated contacts and the component rotating in this barrel, you get a very small grain size at the surface. I mean, they're of the order of 1 micron. And in the bulk, of course, the grain size remains intact. Samples. So we are going to look at the cracks in 3D using Xray tomography, synchrotron Xray tomography. So we unfortunately have to deal with small samples. Small is from roughly a cross-section of 1 by 1. This is slightly under 1, it's 800 micron. It's not a big issue in the sense that we want to deal with short cracks, right? We want to know how they behave when they are sub-millimetric or 500 micron. As I explained, those samples are either extracted from the surface of the cold extruded bars to different strain levels, or directly from the skin, the forged skin of the component, shot blasted or not. We have worked with cracks initiated from artificial defects. This is a strong assumption, this is a strong thing to do, because your cracks do not naturally initiate from defects, which might be defects resulting from the forging. On the other hand, we tried. We spent nearly one night trying to initiate the cracks from a forging defect, and it's not very effective. So you spend time looking for a crack, 4 days at the synchrotron, you lose your time basically. So we decided instead of using artificial defects, there are various ways of doing those defects, from feed, laser, or even electro-discharge machining. That would work as well. We selected laser, which was more effective in terms of time. So it's a femto laser machining. You can see maybe this is the notch seen along the space direction, right? This is the cross section of the sample, the plane of the screen. The notch are 100 micron by 40 or 50 micron, and they are very narrow. The opening is about 3 micron. We did tomography, synchrotron tomography, because lab tomography for fatigue cracks, in spite of the low voxel size, it's really a challenge still at the moment in the lab to be able to fatigue cracks. it's not only a matter of voxel size, it's also the way you're detecting the signal. And in synchrotron, you add on top of the attenuation contrast, you add the phase contrast, which is kind of a diffraction effect, and that helps you a lot in detecting the crack tip. In the lab, you are a bit blind to the really tip of the crack, A, and B, in the lab you're using a divergent beam so that your machine or your sample has to be as near as possible to your X-ray source to keep the voxel size below 1 micron. So that's a challenge for the machine itself. In the synchrotron you use a parallel beam, so you have as much space as you want near it. Okay, so important numbers are given here. We first, at the synchrotron, used a stress ratio of 0.1, and I'll come back to that later. That's an important parameter. This is the machine. A quasi-monochromatic X-ray beam of 60 kV. They call it pink beam. It's not exactly monochromatic. It has some delta, lambda over lambda of the order of 10 to the 1, minus 1, sorry. That gives you more photons, more flux. So you can record the 1000 radiograph for the tomography in slightly less than 4 minutes here, but it can be much quicker. I mean, you could do it in 45 seconds, for example. It's not a big issue for us here. It might be if you are, for example, doing fatigue at high temperature. You need to go quickly to avoid creep effect, for example. And the voxel size is the also important number. It's more or less the spatial resolution. It's 0.7 micron here. Actually, as a rule of thumb, the spatial resolution is twice that number. So we have the spatial resolution, which is of the order of what you can get from optical micrography. So this is what the crack looked like. This is an example. This is in the connecting rod. This material has been shot blasted. This is the shape of the crack projected along the stress direction. So what you see is the crack front here. I told you that it was quite dull, no strong interaction with the grains or any microstructural features. This is the crack at the surface and in the depth. So to check the accuracy of the measurement, what we did was to measure the crack length at the surface by optical microscopes and check what we had in the tomography, and we got a comparison which was the same at 1% with accuracy, more or less. So we have good, we are fairly confident that with tomography we are observing the crack under load, fully open, that we can indeed detect the crack as with a resolution which is comparable to optical microscope. Okay, so here we go, material number 1. Those are the crack fronts. You see that there are some defects at the surface coming from the forging or the extrusion, but those defects are not able to initiate the cracks, unfortunately. All the cracks start from the notches. They tend to develop very gradually, and very soon they have a crack front which is fairly regular. I mean, even if, so the size here is 100 micron, so as soon as they are 200 micron long, then there is not much interaction with the microstructure. So, a bit disappointing from that point of view, to me at least. I was used to other types of cracks. Material number 2 is fairly the same, unfortunately. It's really perfect half-penny shape, nearly, with an angle here which is close to 90 degrees. And again, different microstructure. Actually, in that case, it's a different strain level, but a very regular crack front. So to make it look a bit different, Pablo put them in black and white, but unfortunately the message is the same. For material number 3, it's pretty much the same, right? So very regular crack front, and not much interaction with the microstructure. The only difference we got was from this one, which is material 4, and I'm not sure you can spot it at once. There is a difference in the angle that the crack front makes with the surface, which is now no longer 90 degrees. And the difference it makes is that the crack aspect ratio will be different in this case. Right, before going to the crack aspect ratio, a few more quantitative data. This is the crack depth, A, or the crack length, C, divided by 2 at the surface. So full samples are depths and empty hollow samples are the crack lengths at the surface for two different load levels, and you see that the curves superimposed, telling you that it's indeed a half-penny shape, and it doesn't depend on the stress level. Same thing for material number 2. Maybe one difference is that you get cracks a little bit later depending on your strain level in the material. Again, I mean, this is exactly what we saw when we looked at the pictures. The cracks are very regular, and their shape is, I mean, you could predict the depth looking just at the surface. This is what it tells you. For material number 3 and 4, there is, however, a slight difference. It's, again, nearly the same thing for material number 3, where the two curves superimposed quite well, except maybe here at the beginning. But the main difference is for the red curve, where you do get a difference between the hollow symbols and the full symbols, telling you that indeed there is a difference in the crack aspect ratio for this material, which we don't for the other, which we don't have for the other. In terms of crack propagation rate in the Paris formalism, what does it give us? So you have two things to decide: how you are going to measure your crack size, because of course you have plenty of points. So this here is the square root of the projected area, but you could do it differently. You could use the depth or the surface length, but they basically all give the same result. And the delta K is obtained from the Murakami formula, based again on the projected area. You see that there is not much difference between the two curves, which correspond to two different area reduction, called force. And for 3 and 4, it's even worse. I mean, they superimposed almost perfectly. So really, you could say at that stage, there is no large effect of the surface condition or the forging process on the propagation of those short cracks. Now, as I said, we did see a difference in the crack shape in that case and not in the other ones. They are all summarized here. I think maybe when you compare them on the single slide, it's more obvious than what I said before, that the angle is slightly different in that case. So in terms of crack ratio, this has an influence. This is for one sample for each material, the evolution of the crack depth over crack length ratio as a number of fatigue cycles, but this is normalized by the number of cycles to fracture. So this is the end of the life for all samples. So you see gradually it increases and it levels off a value which is centered around 1 here, but one sample or one material is markedly different and it's below. So if you study this value, which is the steady state crack aspect ratio for different samples of the same material, you see more clearly the trend. For material 1, 2, and 3 are above 1, while clearly for material number 4, for those 7 samples, you are clearly below. So there is a change in the crack aspect ratio for this material. And this was, I think at that stage when we went to Urbino, this is where we were. So we have no real idea of what was going on, except maybe what you all have in your heads probably about the variation of the stress intensity factor around the crack front, which is the Newman and Raju typical formulas, right? If you compute the K value along the crack front, this is one surface, this is the other one, this is theta, the angle that describes the whole crack front. In the interior, your stress intensity is lower than at the surface if your crack aspect ratio is 1, and if you go to 0.8, this is more constant. Well, it's not perfectly constant, right? And this is supposed to be the equilibrium shape for a crack, where you grow your crack front at a more or less balanced values of the stress intensity factor all along the crack front, right? But in that case it was puzzling, because we had an out of equilibrium shape for most materials. Only material number 4 was showing something like this. So what Pablo did, because at that time we started discussing the effect of crack closure. Unfortunately, we couldn't go back to the synchrotron and do more experiments at different load levels, stress ratios. So what he did, he tried to do one experiment in the lab, cycling the sample at a different load ratio, and then just breaking them open after the crack had propagated. So of course that gives you only 1 point. That's very poor data, but that eventually that gave some very interesting results. So the stress ratio in that case was 0.5, and after a given number of cycles, the samples were broken open. So you can see the brittle fracture surface here, and it's not that difficult from SEM, using SEM to find out what was the crack front at that time. And if you compare now the 0.5 with 0.1 values, you do see a difference. For 0.1, this is material number 3. You remember the crack aspect ratio used to be 1. Now, if you cycle at 0.5, the crack front that we have is the red one, and this is much closer to 0.8. In fact, this is 0.8. And if you do it again for a different sample, because Pablo was kind of, he was doubting a lot. So he did it again and again. That's the same trend. If you cycle at 0.5, you break the sample open, compare that with the synchrotron experiment, then you get a difference where your crack is, if you normalize by this depth here, your crack appears longer at the surface using a higher stress ratio. While if you do that for material number 4, which is the one which had the 0.8 crack aspect ratio, whatever the stress ratio R, you get the same crack front. So in blue, synchrotron experiment, and in red, the lab experiment breaking the sample. So you get an evolution when you move from 0.1 to 0.5 for material 3, and no evolution for material number 4. So if you look at it from this graph, those where the values are equal to 0.1. Now if you go to 0.5 for this material, you went down to a more equilibrium shape for your crack front, while for material number 4, you stay there, right? There is no influence. So what's going on? Well, we believe that this is because of crack closure and the evolution of crack closure around the crack front. This is a well-known picture of the plastic zone close to the crack tip in a through crack in that case, which is smaller in the bulk and larger at the surface because you go from plane strain to plane stress. And this is very well known, in fact, and when you draw this crack in a CT sample, you get crack tunneling. All of you know that. And the crack at the surface is held back by larger crack closure. There are less evidence of this on pass-through crack. There are a few data on aluminum alloys, but not much. And we believe that this is what we have here. So if now I'm discussing what we get, if for material 1, 2, and 3, for R equal to 0.1, we believe that we have some surface closure, which is larger than the bulk one, even if the samples are smaller, and that we do get some tunneling. It's meaning that the crack fronts are held back by some closure here. If then you, and the result of that is that your crack front is nearly, your crack aspect ratio is nearly 1. Now if you increase the load ratio, you release this crack closure on the surface, and your cracks start to grow with a 0.8 the crack front ratio. Now, why is it so different for material number 4? Well, you might remember that in this material, you have a microstructure gradient. You have smaller grains at the surface. This is at the scale here. So, more or less on maybe 20 micron, you get smaller grains. And we believe that they are quite effective in increasing the local hardness below the surface. And if you have a higher hardness, higher yield stress, then you have a smaller plastic zone probably at the surface. And a smaller plastic zone, if you assume that the closure that is there is due to plasticity effect, then the closure effect should maybe be smaller or reduced at least. Okay? So in that case, going from 0.1 to 0.5 should make no big difference, which is indeed what we see. Okay, so what is the conclusion of all this? The first important conclusion, even if it's not so obvious, is that it is indeed possible to watch the cracks growing in 3D in a material like steel, which is a strongly attenuated material. Usually we work with aluminum, titanium in some cases, but it's harder. But still now it's feasible, and that was also a good result, even if for the case we studied, we had no large effect of the process on the crack shapes and the crack forms, except on the crack aspect ratio, which we explained by a reduction of the surface crack closure due to this microstructural gradient induced by the shot blasting at the surface. But apart from this effect, which is, I must say, not so big, we found that there was very limited effect on the crack growth rate of the small cracks from the different forging conditions that we investigated. And I think on that. Thank you.